Hello everyone, this is Mr. 13 Things, aka also known as Silence Did Good. And I am here now working on kind of my final project, if you would, for the Expel grant. And what that is coming up with a final set of short tutorials and then actual recursive exams based on the Khan Academy exercise framework to pass on some what I consider base knowledge ostensibly to my two daughters, who are great kids, very sharp, that come from a couple of wonderful lineages, that have a lot of opportunities and a lot of potential, but that are entering a world where in fact they will have missed this, at least in their formative schooling years, this massive online courses and this kind of sharing of creativity that Chris Anderson talks about, the TEDification of the world, if you will. And so what I'm going to cover here is one of my sets of 13, which won't turn out to be 13, but we're going to talk about coordinate systems here. And let's see if I can do that. So we're going to talk about coordinate systems. And where this is coming from, why is it coming at this point, is we just talked about the concept of parametric equations. Parametric equations, where in effect, the ones we were talking about, things are a function of time. So multiple things are a function of time. And time doesn't go backwards, and so there's lots you can think about there. And in fact, things do not have to be a function of time to be a parametric equation. They just have to be a function, two things have to be a function of something else. But in this case, this really works pretty nicely to start talking about animation, and it starts to be, for me, the most logical place to jump your kids from, to say they can see the interrelationship between math, music, and computer science. And the computer science, typically this will be animation. All right, so the coordinate systems. And here's the rub. If we keep our kids in a typical XY coordinate system their whole lives while they're playing in 3D, we're missing out on this incredible opportunity. We need to take them into, instead of an XY coordinate system, an XYZ coordinate system. And very often you'll see we'll add an extra number down here. I'll put that there. But so that we don't let them think that as you start going to an R theta, or what would you call a kind of 2D spherical, we really, at that point, we need to take them into a radius, angle, and we'll talk about what these angles are here. Or in fact, really off of that, another very typical one is a cylindrical, which would be R, theta, and Z. These three coordinate systems, or three types of coordinate systems, tied with animation, give you a lot of power in thought, in terms of animation, and in terms of figuring out. One of the most important things about problem solving is two things. What is your coordinate system? What is the coordinate system? And then what type of it? So what is it? In other words, where is the origin? What is the standard position angle? Or what is the standard, I guess the standard position angle? Position angle, if you would, or position discretion, and what is up? Now, so what is the coordinate system? And then what you'll see later in terms of problem solving is which type of coordinate system. So if we've kept our kids from realizing that the world is in fact 3D on their game sets, and then you can keep track of things in 3 dimensions by 3 components of a vector, and that vector does not have to be x, y, and z. It can also be how far something is away from you, essentially where it is in comparison to what you consider front or side, and where it is as you consider what is up, up being the opposite of down. So basically figuring out what is forward or what is x, and then what is up or down takes you into this 3D coordinate system. So that's a little befuddling until we kind of think about it in a picture. And so I'm going to do this, File, New, and I'm not going to save it, even though I could. And I'm going to now talk about some basic colors that are kind of what happens in the gaming world. And that is when we draw coordinate systems, typically our X is red. Hope I get this right. Our green is Y, and our Z is blue. And so I'll go ahead and change back to white if I can, which I probably can't, so I guess I can. So this is the X direction, this is the Y direction, and this is typically the Z direction. And later on you see you get to choose those, and this in fact is the origin. And so as you pick a particular point on here, I'm just going to go 1, 2, 3. I'm going to put that point right here and express it in 3 different vector formats so you can think about. So that point there is all along the x-axis. Now if you were looking this from straight down, this is what you would see. I'm going to see if I can do that. It would be, of course, now we typically think of the x going this way. We think of the y going this way, and then our point would be 1, 2, 3, would be right here, right? So these are the same thing. I'm going to go ahead and cut that out. Edit, cut. All right. So what are the 3 ways, right? Because if it's in 3D space, you need 3 values of a vector. The 3 ways to describe that point. The first one we're going to do is in terms of typical x, y, z vector format, and that of course would be a value of 0 in the x, edit, undo if I would, 1 and 3 in the x, 0 in the y, and 0 in the z. That's one way to describe that point P1. So P1, alright, that's P1 right there. And this is 0, 0, 0. What's beautiful about the origin, or I better do that in another way so you can see it. Edit, undo. Because we really quickly, if we get into 3D, it's going to help probably a lot of folk as we're in this transition period to start notating our things in vector format. So that origin is 0, 0, 0, and this is P1 right here. All right, so that's one way to express P1. Another one is to express, right, it as a radial distance from the origin, some angle 0 from the x-axis, and some angle phi, which typically is very often is going to be maybe a polar angle, though I'm actually used to learning to do it up from the horizon. This is going to be polar angle, which is down from up. So we'll think about what that is in a minute. So in this case, we see that by golly, the radius is equal to 0. I'm sorry, again, making a mistake. Edit, undo. This is when you have grad students. 3 is the distance from the origin, the radial vector, and we're thinking about the what? The point is actually the end of a pointer. So we're going to put that up here. The point is actually the end of a pointer. And when you make that leap, this is, we're thinking about for like a week. All right, so in this case, your angle from x, your angle is 0, and your angle down here in this case is pi over 2. You've come down 90 degrees. Now we can do the last one, which is cylindrical, and it is r theta and z, interesting to note that in fact these first two values will always be the same on a typical setup. So in other words, if you have it in polar coordinates, this is typically called polar coordinates, you then will have it in, you have to change one value. Wrong. I'm wrong on that, so ignore that, strike that. We'll talk about what this R is. So in this case, as we go to here, playing around with my pen, got my 0 there. Let's see what it looks like now. Too big a brush. I'll screw it up, but I'll go ahead and put, there's my theta. All right, so now, if I go to here, it should be better, equals, right, in this case, it is back to 3, 0, and 0 for the z. However, right, documenting what type of way you're putting these things becomes really important, especially as you start looking at the differentiation between this and this. They look like they're the same thing. So let's look at one other point. So what we're going to do here is we're going to go ahead and climb. We're going to go ahead and put something, let's say we're going to do it here. Remember, we do parallel lines and parallel lines. We'll put a point out there now and think about what that is. So this is 3 and 3. So in this case, P2, we'll call this P2. So P2 equals, in this case, it would be 3 in the x, 3 in the y, and 0 in the z. P2 in the same format. Now let's think about it. It is the hypotenuse, so it's going to be the square root of 2 times 3, so 3 times the square root of 2, 3 times the square root of 2, and then undo that, strike it again, edit, undo. Remember, this is polar coordinates. This is now at an angle of 45 degrees, or in fact pi over 4. And its angle off the up is in fact also pi over 2. And in this one here, remember, it's going to be very often, it's going to be the distance along here, which in this case is true, 3 the square root of 2. It's a little bit longer, right, than in just 3. Its angle is pi over 4, and its z is 0. So, learning to play around with the importance of defining the origin, defining the direction of the standard position, and then defining up is something that is a key part of animation. You'll see very often for this one here, it could also be very typically called an azimuthal angle. Sorry, I'm not going to even say what that is. It can be actually measured either from 0 to pi, is probably the best way to do it, 0 to pi, but you can also going up and down off of the x and y plane. Very often you can see it as from 0 to plus or minus pi over 2. So what we're looking at here within 15 minutes is, in fact, 3 coordinate systems, 3 types of coordinate systems, and to review, they are Cartesian, polar, and cylindrical. And we're looking at them in a vector format so we can parameterize with t. Parameterize with t, and then express any point in 3D space using a variety of vector notations, knowing that certain problems in life are easier to approach when in fact you look at them from a different way or using a different set of tools. The other thing to get out of here is the fact that pretty standard now, red is the defined x, green is the defined y, and z is the defined blue, or however you want to say that. Thanks for listening.